much for attending Barry's lecture. It's my great pleasure to introduce Dr. Barry Bickmore from Brigham Young University. Barry is a mineralogist / geochemist. He's one of the few people in the field who manages to combine experimental work with different kinds of modeling approaches. And in addition to that, a lot of his work also is related to science outreach, public education, pre-kindergarten teachers, education on how science is done, how scientists are creative rather than not just these people in their lab coats. So he's got it all: the experimental work, the theoretical modeling work, the outreach. And he's doing all this at BYU, which primarily has an undergrad program and up to a master's program in this department. So this is without the help of PhD students and postdocs, which is how I learned, right? So, in addition, he has an amazing sense of humor, very witty. So, all, he and I are like twins. Except for that. But Barry and I have known each other, like 10 years, maybe? Yeah. And it just amazes me every time I meet him how, he started from his PhD program at Virginia Tech with Michael Cella, one of the big luminaries in mineralogy. I'm sure all of you are familiar with his name. Looking at doing AFM microscopy of mostly clay minerals, and he did some groundbreaking research on how to look at minerals in the presence of water in the AFM, and how to use different macros to do image analysis and processing and get quantitative information out of that. And also looked at how you relate the structure and reactivity of the edge sites of clays to their acid-base chemistry, dissolution, uptake of different kinds of cations like cesium-137. This was later done during his postdoc. But what amazes me is that he starts from the AFM scale and works his way down to the molecular and atomic level. So he really wants to figure out the mechanisms by which minerals, for their structure and reactivity. So let me just point out a few other important contributions he's made in addition to this groundbreaking work he did using his PhD. One of the other things he's done is the reactivity of minerals, of course, depends on what surface crystal plane you're looking at. And so he was able to figure out a way to quantify the edge site surface area versus the basal plane surface area of a clays. And that's very important because the edge site surface area is very little, but that's where most of the action is happening for the most part. And then he went on to develop this amazing model to explain the acid-base chemistry, the structure of different minerals. It's a broad-based model that can be applied to different minerals. And it's based on bond-valence. This is a concept about the charge on a cation or anion versus its coordination environment. He took into account ionicity of the bond, solvation, the detailed molecular structure around the bond. Now he's even gone up to including some electronic structure theory. And as his abstract says, the neat contribution, one of the amazing contributions here is that this sort of, it's kind of like a force field for molecular mechanics modeling, but the fancy molecular dynamics and mechanics that we do in my group can't take care of chemical bond making and breaking. Whereas this approach he's developing, either he's already published or he's on the verge of publishing this, I believe. So, okay. Let me just see if I have anything else to add here. Okay, I think that's all I want to say, and it's really, we're giving him a warm and cold welcome here to Ohio. Thanks, Barry.
Well, thanks for inviting me. Nita told me that there would be a lot of undergraduates here. Is that true? There's any undergraduates?
Mostly graduates.
Oh, okay. Well, so I've made this really pretty basic, but if I'm losing anybody, just raise your hand and ask me a question. That's fine. So I tried not to have too many slides. This isn't the difficult part yet. Anyway, so so this is my collaborator, Matt Wander, who works with me, and then I have had a couple master's students working on this, but mostly I have my undergraduate army working for me. They do a lot of MATLAB programming and data analysis and that kind of thing. Okay, so I told you I was going to start out basic, didn't I? Okay, in science, you have different kinds of models we use. So there's conceptual models that just sort of put the concepts together and link them up, and you can think about a subject in different processes. There are physical models. You have some of those. Somebody was telling me about that today with little sandboxes and all that kind of stuff here. So you can use these things, conceptual models and physical models, to sort of get an idea what might be going on in the real systems, or just to think about the whole thing. At some point, hopefully, you put them into a mathematical model. Okay, so when you get to that point, then you can run these things on supercomputers or whatever, and you can have all kinds of different sub-processes going on, and you can see how they interact and so on. And this is really important when you get to that level, because modeling, I found out late in graduate school how important modeling is, because I had all this data, and you want to write your dissertation then, but what do you write? You have to interpret the data, and I found out that I couldn't ever get enough data to really tell the whole story. I had to fill in the gaps with models. Because we can never just, if you're an experimentalist, you know that there are a lot of experiments you would love to do, but either they're impossible at the present state of technology, or they're too expensive or time-consuming, so that even if you can do them, you can't do very many of them, and things like that. So this is really important. And like I said, models can help us see how a number of relatively simple parts, we can simplify systems and experiments and things like that and quantify them, but what about when you put them together into a really complex system, like microbes or whatever interacting with the mineral surface? That's unbelievably complicated, even though it's on a very small scale. Now, one of the things I do is molecular modeling. With molecular modeling, you're just modeling how atoms and molecules interact together. And you can get all kinds of useful information from that at the macro scale. Well, you can look at smaller scale things like the molecular structures of minerals, or even proposed phases. One of the things you can't do is dig a hole to the mantle, for instance. And so some people model possible phases that could be there in the mantle, so they can interpret the seismic data, which is really one of the only ways we can look at certain parts of the Earth. We can predict thermodynamic properties with these things. So this is just a SiO2 phase diagram, but you can predict thermodynamic properties of different structures and then map out phase diagrams and things like that. You can also figure out what reaction mechanisms might be in play, which turns out to be really important because for a certain starting and end point, there are often multiple pathways to get there, and the rate of the process depends heavily on the pathway. And so mapping out things like molecular scale mechanisms of reactions is really, really important for predicting and interpreting kinetic data, so how fast reactions happen. All right, so if you're going to do molecular modeling, the gold standard, what you really want to do is use a quantum mechanical model. There's various levels of that, but hopefully you're all familiar enough with this. These are just some atomic orbitals. And really what all these are is they're describing the distribution of electrons around a nucleus as a 3D standing wave wrapped around a point. Okay? So, and that's where you get these different shapes, if you didn't know that before. They're just 3D standing waves. And that's why the energy levels are quantized, because you have to have a whole number of wavelengths wrapped around in order, so it won't cancel itself out. Okay, so that's all that is. Very elegant theory, beautiful theory. Mathematically, it's not ridiculous, okay, at least at its simplest level. But then when you get to molecules and you know, condensed phases and things like that, it gets more complicated. Because now what happens is you take the valence orbitals and they reconfigure themselves to be 3D standing waves around multiple points. Okay? And the mathematics for that is complicated enough that you can do it on a PC, but only for very small molecules that don't have a whole, not very heavy atoms, so they don't have a lot of electrons. You can do somewhat larger systems on a supercomputer, but if you think about the systems of atoms that, for instance, geochemists are worried about, you have to have a lot more atoms to represent that fully, or even close to fully. Okay, and so you have to have much bigger systems of atoms, and you just can't do that, or at least you can't do everything you need to do with quantum mechanical calculations, because they're too intense on the computer. Okay, we don't have enough time or memory on the computer to handle that. So we come up with cut rate ways of doing this, where we can use bigger systems of atoms and get the kind of thermodynamic information and so on that we would like. And the typical way to do this is called molecular mechanics. Okay? And what that is basically treating the atoms as balls on springs. And so here's my spring here, and this is Hooke's law, and this is the transformation of Hooke's law to potential energy. So it's just force equals some constant times, this x is just the deviation from the equilibrium position of the spring. Okay, so you have the force, which you can calculate just by having some kind of energy cost for deviation, and then you have you can have the energy too. But this is just deviation from some equilibrium point, and then you have some way of calculating an energy cost function from that. This is unbelievably simple, simple-minded even, but a lot of times that's what you have to do when you're modeling. You just boil it down to some ridiculously oversimplified level and just see how well you can make it work. So with molecular mechanics, what you're doing is putting a bunch of springs on your atoms and on your bonds and things like that, and then you don't use, well, sometimes they do use Hooke's law directly, but most of the time you are changing Hooke's law to mimic the quantum mechanical behavior a little better. And you can't do everything. Certain types of spectroscopy you can't obviously do when you're not even representing the electrons. And so there's a lot of things quantum mechanics can do that this can't. But still, it's a very useful tool. So here's sort of what I was describing. Generally, the architecture of a molecular mechanics model is. So a molecular mechanics model, by the way, is called a force field, which makes it sound way cooler. Okay, so you end up, what you have is structural descriptors. You have to have some way of describing the structure of the atoms that you put together, okay? And so typically, bond lengths, bond angles, that kind of stuff can describe the structure completely. Or at least the relative positioning of the atoms, even if you're not worrying about the electron density. And then you have to have predictable ideal values for those structural descriptors. So maybe you'd say, oh, this type of bond likes to be this length, or if it can, right? And this type of bond angle likes to be this angle, so on and so forth. So then when you have that predictable ideal values, you apply energy cost functions. There's various forms that those can take, but it's all based on deviations from the predictable ideal values. Okay, so just like with Hooke's law, we had x equals 0 was our equilibrium spring position, and then x was just the deviation from that ideal point. And then we applied some kind of energy cost function by multiplying by a constant and squaring the deviation. Okay, so that's the basic architecture. So once again, in a normal molecular mechanics model, so where do you put the springs? Well, you have bond stretching springs. So you say these two are bonded, so let's just put a spring on them, and I'll show you the form that usually takes. You might have a spring in between these two bonds here and have an angle bending term. Okay. You might even, especially if you have organic systems where you have some pi bonding or something like that, you might have a torsional spring where you're basically putting a spring on the twisting angle of that molecule. And then you have some non-bonded interaction. So maybe there's some kind of net charge on these, so they would interact via, you could use Coulomb's law or something like that. Van der Waals interactions, that sort of thing. Okay, so okay, so this is basically what a normal force field might look like. So this is just the this is a Leonard-Jones equation. So this is Van der Waals forces, and this is basically what the function looks like so this is distance right here between these two atoms, and here's the energy. So there's a place right here where it's happiest, right, and then it's not happy. Energy goes up if you move too close, and but more gradually goes up as you move away. Okay. This is just Coulomb's law, if you recognize that from physics. So depending on the charge of the two atoms and their distance, you can predict some kind of force or potential energy between. This is a bond stretching equation, I guess, or term right here. And do you recognize this? It's just Hooke's law. And like I said, sometimes they actually do just use Hooke's law to represent bonded atoms. But if you have Hooke's law, you can't dissociate the two atoms, so you can't break bonds if that's the case. And look at this for this angle bending term. It's Hooke's law. What do you know? So, and then for the torsional term, sometimes you'll have these weird cosine or sine functions and things like that. But in any case, this is the basic architecture of a molecular mechanics model. You have to have terms, you have to know these sigma values here and this epsilon value here, and you have to have ideal values for the different kinds of bond lengths and different kinds of bond angles, and that sort of thing. So the number of terms you have in this model can sort of grow exponentially by basically to the second power, the more the types of atoms you include. Okay. So here are some problems with molecular mechanics type of model. I already mentioned it can't do everything that quantum mechanical models can, but every model can't be good for everything, right? So one problem, in addition, though, is that there isn't really a single ideal bond length or bond angle value for a given bond type. So you can imagine, hopefully you learned this in mineralogy or something like that if you took it. If I have a structure, say with a silicon here, and I have 4 oxygens around it, and if I shorten this bond, okay, the other bonds will want to lengthen. So what the ideal value of a given bond length is will depend on what else is going on with the atoms that are bonded to the 2 atoms that you're looking at, right? So the upshot of this is that if you calculate a structure, so optimize some structure of a molecule or a crystal or something like that in using a molecular mechanics model, they tend to be too symmetrical. All the bonds want to be the same length if they can. But it's really not like that because of this problem, okay? Also, you can't really do coordination number changes. So for instance, if you have a 6-coordinated silicon versus a 4-coordinated silicon, the bond lengths are going to be different, okay? So you, in a molecular mechanics model, a typical one, you have to define different atom types for a 4-coordinated silicon or a 6-coordinated silicon, okay? And you can't change the coordination number of that atom because it's defined as a 4-coordinated silicon or a 6-coordinated silicon. So if you try and model some kind of reaction that would involve a coordination number change, you can't even go there, okay? All right, so all of these little parameters in our spring equations, they start adding up. And they're not something that you know in advance. When you add more different types of models, or different atoms to the model, you actually have to take that into account and refit everything as far as these adjustable parameters in the model. And so as you add more types of atoms to it, it goes up, the number of parameters in your model goes up at least to the squared power of the number of atoms, okay? Now, you actually can do molecular mechanics models that allow chemical reactions, but that requires typically an enormous number of parameters. So I'm familiar with one model where all it does is water, okay? 2 elements, and it has 21 adjustable parameters. Now when you have that many adjustable parameters that you're trying to just empirically fit your model to some data to calibrate it, what happens is you can fit the data pretty well, usually. But when you then take the model and try to apply it to a slightly different system, it's not very transferable. So you have to be really careful when you do one of these studies to benchmark your system on things that are really similar to what you're interested in. Otherwise, it could be complete junk that your modeling information that you get back. Okay, so there's an exception to that though. There are some force fields that are rule-based, meaning all those parameters I showed you in the energy cost equations, they will take things like atomic sizes of ionic radii and electronegativities and various tabulated quantities like that you can get for all the atoms. And they will sort of do some kind of correlation where they can predict about what the parameters in the standard model should be like. And so in those cases, you can do the whole periodic table. You can add, over 100 types of atoms in there. And it works sometimes okay, right? But it's just not good enough. Like I say, they generally suck.
Very scientific term.
Here's the equation for suction. No, I'm just kidding. Okay. Now, another problem is that the models, again, what you do is you have some data that you want to calibrate it on, so you adjust all your parameters so that your model will generally reproduce that. And I guess I already mentioned this, but re-emphasize that. A very narrow range. These are usually very, very narrowly applicable. So, for instance, if you're interested in organic molecules, there are so many force fields for organic molecules, and they're mostly for very specialized purposes. There's some general purpose ones, but they're not going to be as good as the more specific ones. Okay, so there I was this experimentalist who is gradually moving into modeling. Surface chemistry is my main deal. And I figured out that we could really use better molecular mechanics models because the kind of experimental information we get is usually sort of averaged over larger areas. just not specific enough to get down to molecular mechanisms and things like that with a whole lot of confidence. I mean, you can make some inferences and so on, or guesses, but it's hard to tell whether your guess is really that reasonable or not. So what we decided to do was back up and sort of take another approach to the whole molecular mechanics type of thing. So we decided to use the bond-valence model. So if, I don't know how many of you guys are geologists and how many are polymer people, but...
Zero polymer.
Zero what?
Polymer.
Zero, oh, okay. Well, so if you're a geologist, you probably learned this in mineralogy at some point, I imagine. Okay, but just to go over it, the valence of an atom is a measure of the number of valence electron states that are available for bonding. And usually it's taken as the oxidation number. So if you have iron 2+, its valence is 2. And what that means is that it would like to form, it could form up to 2 single bonds of polar bonds. Okay. Now, the bond valence is the number of electron pairs involved in a given bond by sharing and or electron transfer. There's sort of a continuum between them. So it's equivalent to what you learn in freshman chemistry as bond order. But in this case, we're defining it as being related to bond length. Okay, so we come up with equations to relate the bond order to the bond length, and that's what bond valence method is all about. Okay, so the bond valence of a given bond. When you do freshman chemistry, you're used to single bonds and double bonds and triple bonds, and that's a lot of what there is. For organic molecules and things like that. But in a crystal, it's more spread out. You don't have to have a whole single bond. You could have half a bond or something like that, or half an electron pair worth of bonds, I guess. Okay. So here's the typical equation. There's no theoretical reason why the equation has to be this way, but this sort of works for crystals at least most of the time. And all it says is your bond valence is equal to e to this power, and this is just the length of a single bond minus the length of the bond you're looking at, and then all that over this b parameter, which just has to do with the curvature of the curve. So it's just an exponential decay curve with distance. Now this is the governing principle of the bond valence model, and that is called the valence sum rule. It's basically just Pauling's second rule, if you're familiar with that. So remember Pauling said that, well, if you have a, let's say aluminum +3 cation, so it has a valence of 3, and it's surrounded by 6 atoms, then 3 divided by 6 means that you have half a valence unit per bond, okay, on average. And all this is doing is just sort of updating Pauling's second rule so that it can handle distorted structures as well, okay? So that's what this says. You sum up all the bonds incident to some atom I, okay, so the valences of all the bonds, and it should be equivalent to the atomic valence, which is the EI there, okay? So this, once again, is an incredibly simple-minded model, okay? Way oversimplifying the real picture of what's going on, but it turns out to work unbelievably well, okay? So here's a part of a corundum crystal, and like I said, this would be half a valence unit each for aluminum +3 surrounded by 6 oxygen. But then if you distort that structure with this bond valence equation, you can calculate what each individual bond would be in terms of its bond order. Okay. The great thing about it, though, is that if we use bond valence as our framework for our structural descriptors, instead of just bond length or bond angles or something like that, it's inherently multi-body. And what do I mean about that is, by that, is that if I have, like I said, this bond right here, if I shorten it for some reason, these other bonds will want to lengthen, okay? And the valence sum rule predicts that, right? So if you shorten this, you're actually increasing the bond order, and so these have to have a lower bond order in order to satisfy the valence of that atom. So this one problem that we discussed before, that's inherent in the normal way of doing molecular mechanics modeling, is not a problem here. So that's why it's intriguing. And people have done bond order potentials, they're called, for molecular mechanics modeling before, but what they really do is take a regular molecular mechanics model and then throw in another bond order term to sort of make it a little less crummy. But there's more parameters, right? What we're trying to do is strip it down and have only bond valence related terms for the most part, okay? So just returning back again, I've updated this little thing to say bond valence based structural descriptors, that's what we need. And we need predictable ideal values for those. And then we need to apply some kind of energy cost functions for deviation from these ideal values. So that's our goal here when we're trying to create this new bonding model that we can transfer to a molecular mechanics type of setting. So here's the basic plan. So we're going to fix and expand the bond valence model, and we're going to create this potential energy model or force field. And at the same time, though, we are sort of taking a dual pathway here, where we're also exploring periodic trends in these kind of structural descriptors, so that at some point we could make more rule-based type of force fields that would be a lot easier to add more and more and more atoms to them. So you're not so restricted in the number of types of atoms that you can have. And even if that is a crummy way to go about it, this would be, having a rule-based system would also make it easier to just come up with initial guesses for your parameter values that you can then adjust to the experimental data. Okay. But it really helps when you're building a complicated model like this to have some idea of what the parameters should be to begin with. Okay, so I said we were going to fix some problems with the bond valence model and expand it. So one problem with the bond valence model is that it only addresses bond lengths. So it doesn't address the angular distribution of bonds. So for instance, here I have my octahedron of oxygens around this aluminum. And here's a nice perfect octahedron, which is similar to what you normally see. But if I don't change the bond lengths and I just shove them all to one side and smash all these oxygens together, the bond valence model can't tell the difference, right? Because it's only about bond lengths. It's not about the distribution, the spatial distribution of bonds. And it gets more complicated because, I mean, with some things, some systems, you can just assume that the atoms will sort of more or less symmetrically distribute themselves around the central atom. That works for a lot of cations. But it doesn't work for anions like oxygen in this water model because you have non-bonding valence electrons that take up space on the surface of the atom too, so you basically have lone pair effects. So that's why this water molecule is bent rather than the hydrogens getting as far apart as you can. So this is called a non-centrosymmetric distortion right here, where you're not stretching it or squashing it or something like that, you're making it sort of lopsided. Okay. Now, maybe you're also familiar with the Jahn-Teller effect. For transition metals that have unequal distribution of d electrons in the d orbital or d subshell. When you have this unequal distribution of these electrons, because the energy levels are split, so they're not all at the same energy level, you'll have certain directions that are preferred for the ligands coming into the transition metal. And so you can get, for instance, in this octahedron, squashing or stretching. Now that's a centrosymmetric distortion because it's sort of the same on either side of the center point, okay, rather than twisting or bending or something like that. Okay, so how do you describe that kind of stuff? Remember I said the first thing we need is structural descriptors, and the problem is that with bond valence, well, we can get at bond lengths, but not the angular stuff. So how do we transform the bond valence model into something that can do angles? Okay, so what we decided to do is called a multipole expansion. Okay, so let me go ahead one slide to explain. Maybe you're more familiar with this. This is a Taylor series expansion. Okay, so hopefully you remember this from calculus, or you remember the name from calculus. That's about where I am, right? So, for instance, this function e to the x, which is this blue line right here, we can approximate that using this Taylor series expansion, which is basically, you know, these terms. Here's a zero order term, a first order term, a squared term, a cubed term, and it can go on and on forever, right? And if you watch how many terms there are here, as it gets higher and higher, the better and better it approximates this function. So that's what you can use a Taylor series for, is you can just have some function, any arbitrary function, and you want to at least approximate a certain part of it or something like that. You can use a Taylor series to approximate it closer and closer and closer the more terms you have, and you decide where you want to cut it off, basically, before you have an infinite number of terms. But that's basically what it is. Okay, with a multipole expansion, that's what they do for the spatial distribution of things that involves angles and things like that. So, for instance, they'll do multipole expansions on the distribution of electric charge in a certain area of space, or they'll do a multipole expansion on the certain or on the mass distribution in a certain area of space. So, astrophysicists and things like that will describe the distribution of mass in a, some kind of what are the big cloud things? Nebula. Okay. In a nebula or a galaxy or something like that in terms of a multipole expansion. Because what it's doing is that the more terms you have in the multipole expansion, the more exactly you're describing the spatial distribution of whatever. Okay? And you just decide to cut it off. And really, some galaxy out there, if we treated it as a mathematical point in space, and just calculated the gravitational forces between us and that galaxy or something like that, we would be really close because we're so far away. As we get up closer, the exact spatial distribution of the mass will matter more and more. Okay? So anyway, in a multipole expansion, you can again go out to infinite terms, but we've cut it off at 3 terms. We have the monopole and the dipole and the quadrupole. So the monopole is just basically, you define some region and you say, okay, how much stuff is in that region? And for us, that would be how much bond valence is reaching a given atom. The dipole would be how lopsided is that distribution. And the quadrupole is sort of, you can think of it as describing an ellipse that you fit around the distribution, so it's sort of how spherically symmetrical it is. And in all these higher order terms, you can actually take what's called a norm of them, even though this is a vector and this is a tensor. And you can boil it down to one number. All right. So the next step was finding predictable values of these things. So this is actually the dipole moment for the bond valence around an oxygen atom, and it was something like 178 oxides that we And this is just the valence of the strongest bond reaching the oxygen. And just on the basis of this, we could, get some reasonable predictions of what the dipole moment of the bond valence was on these atoms due to the lone pair effects, okay? So you're going to expect some scattering because there's other forces going on besides what controls bond angles. But we also wanted to see if we could predict anything better than that, because it was a little scattered, right? So we did a study of molecules where we had two things bonded to an oxygen with single bonds on both sides. So all of these have the same bond valence. This is the dipole moment again. So this is basically lower angles, and this is 180 degrees down here, and this is the Pauling fraction ionic character, which is just based on the difference in electronegativity. And you can see really systematic change in the bond angles depending on the bond character, so how ionic or covalent the bond is. If they're more ionic, they tend to spread out to 180 degrees if they can. If they're more covalent, they end up here, okay? So this is around where water is, 104 degrees to 115 degrees or something like that. So I'm going to skip this, but here's a sort of mathematical model I came up with to describe this over the whole range of valence. But in any case, don't have time for it. So for the dipole, the quadrupole moment, which is, remember, looking at how spherically symmetrical the distribution is. So these are just some standard configurations where we calculated ideal configurations where we calculated the quadrupole moment norm right here, so 1.15. If it were a completely spherical distribution, so if you fit an ellipsoid through it and it turns out to be a perfect sphere, then the quadrupole moment norm would be 0. So that's just showing what the different values would be. But what this is really good for is looking at centrosymmetric distortions. The dipole moment controls for how lopsided it is, right? So that would be non-centrosymmetric distortions. But centrosymmetric distortions like Jahn-Teller distortions, you can describe and predict using the quadrupole moment. So this is the quadrupole moment norm, and this is for iron 3 and iron 2. So the crosses are iron 3, and they just sort of, no matter what this is the fractional strongest bond valence. So a quarter of the bond valence reaching the iron is taken up by one bond, basically, is what this is saying. So in any case, in this region right here where you're going between 6 and 4 coordination, well, it's just staying around 0 for for the iron 3, which is what you would expect for high spin iron. It doesn't have unevenly distributed electrons in the D subshell, so you don't expect Jahn-Teller distortions. But iron 2, on the other hand, you do expect some Jahn-Teller distortions because it does have unevenly distributed electrons in the subshell, the D subshell, and so what you see is going from 6 coordination up toward 4 coordination. It goes up and up and up and up. Okay, so we can define for a given transition metal, we can define preferred distortion pathways, and the bond character does come into this as well, somewhat, but we're still working out the math for that. Okay. Yep. 5 minutes.
No.
Oh, you have a question?
Actually, we started doing
You have till about 1. There's a class in here at 10
Okay.
past, so.
I'll talk fast.
But I was going to ask you a quick question.
Huh?
I'm trying to get my head around, and this is a terribly naive question, I'm sure. But why doesn't it go through the origin?
Let's see. Because I don't have any structures over here. So 0
right,
would
yeah.
basically mean that.
But the data don't slope through the origin is what I'm getting at.
Yeah, this would be a free atom right here, the origin. So I didn't.
Fair enough.
No point to that, but yeah. So it took me a long time to start thinking in valence space.
Valence space.
I like saying that too. Just it's makes it sound
Sounds
cooler.
mystical.
Okay, so another problem with the bond valence model is it's calibrated on crystal structures. It doesn't work as well on molecules. These are some oxide molecules where we had single bonds in them. Just by definition, using the valence sum rule, you would say, okay, an LiO-Li molecule has two single bonds, right? And then we used the bond valence equations that had been calibrated on crystals to calculate what the bond valence is, and looked at the difference between what we knew it was really supposed to be and what you would calculate using those equations, and as a function of the fraction ionic character, so the bond character again. And we find for single bonds and double bonds, just really systematic deviation from what they should be, which is right at 0, both of them, as you get to more and more ionic bonds. So in order to pull this off, we needed bond valence equations that were applicable over a larger range of bond lengths, because we wanted to pull apart bonds, we wanted to smash things together and look at transition states and things like that. So we needed equations that could handle a bigger range. So this is one of our equations that we use, so sort of more along the same lines as the other one, but it has 4 parameters instead of 2. Okay, the next problem was the classical bond valence model. Like I said, it only addresses polar bonds because you're using the oxidation state as the atomic valence. But it's not always like that. For instance, this is a pyrite structure, and it's FeS2, right? So it's iron 2 plus and the sulfur minus 1, okay? So it's minus 1 not because it only wants to form 1 valence unit of bonds. It does form 1 valence unit of polar bonds with the irons, but there's also a 1 valence unit fully covalent bond. But in the classical bond valence model, we sort of ignore the existence of that kind of stuff and work around it if we do anything at all with it. Which is kind of bad considering how common for sulfides are. So anyway, what we ended up doing was looking at using cation and anion bond valence calculations and fitting this to a bunch of crystals. Well, basically what this graph is a cumulative distribution graph, so or cumulative distribution function. The tighter it is to this 0 line, the better the fit to the data. We found out that if we include oxygen-oxygen interactions in our bond valence model, we actually got a lot better at getting rid of outliers and things like that. And now you do fully covalent bonds and also have a means of keeping the oxygens apart in a bond valence type of framework for molecular mechanics. Another problem with the bond valence model is that I said we need energy cost functions, but nobody has any idea what they should look like. It's astonishing, and I've done this too, but how many people have used bond valence as a descriptor for use in energy models? Nita's done this, right?
Sometime in my past.
Yeah, I've done this. It's actually very popular, and it works well enough that you know there's got to be some smoke. I mean, there's got to be some fire because there's enough smoke, right? But when we started fitting our first force field, we found out that it's complicated what these things should look like. And we verified this by looking at known bond energies of diatomic molecules and atomization energies of crystals and things like that. You get, depending on what type of bond it is, the energy versus bond valence curve can be quite different, okay? And I don't have time to get into all the upshots of this, but these curve shapes actually explain a whole lot of chemical behavior. Okay, so Matt Wander has been busily for months doing our first force field, and I said, hey, send me some slides of the results, and then he didn't label them, but here's what it is. We had a bunch bunch of crystals in the system where we had aluminum, silicon, hydrogen, and oxygen. So we got all the crystals and actually molecules and things like that where we had good structures and we had thermodynamic data. And this is predicting the delta G value for each of these things. And this goes out to free atoms, hydrogen molecules, stuff like that, are all in here. We calibrate the model, so this is the calibration set of structures. Here's the calculated energy using our model, and here is the real energy, the measured energy. And the blue symbols, which you can't see on this, are just using the bond-valence terms, so the monopole, basically. And this red is using the dipole as well, okay? And you can see, it actually makes it a little more accurate to use the dipole term, but it is incredibly accurate. If this keeps working, we have a lot of stuff to do to see how well this ends up working. But so far, this is working better than a lot of quantum mechanical calculations on a system of 4 atoms, which isn't bad. So we saved some of our structures to check how good the fit was on them, even though we weren't calibrating on them. And still, we're getting really good results over a really wide range of energies. Okay. So, like I said, we're at very preliminary stages of this, but this is what we're shooting for. That's why I have unicorn with rainbows and sparkles and stuff like that. This is what we hope will happen. We don't know how far we can get with this. So far, so good. But hopefully we'll have force fields that can handle both polar and fully covalent bonds. And metallic bonds are a different beast, and we don't know yet how well it would work for that. They can do chemical reactions, so we can pull things apart, and we can have coordination number changes, and go from 4 coordinated aluminum to 6 coordinated aluminums, which happens in solution, so we can model all kinds of stuff, we hope. We could maybe even do redox reactions with, we think, okay? And also look at Jahn-Teller distortions. We can even detect spin transitions, meaning when the electrons jump between the d orbitals and it changes how it wants to distort, okay? We should be able to use this on organometallics and organics. And like I said, how successful this is will depend a lot on, and how broadly applicable it is will depend a lot on how we can develop the rules of the bonding model so that we can predict in advance what the parameters of the model should be. But then if we can pull it off, we'll have better models than anybody out there for molecular mechanics type of framework. So hopefully there's a couple minutes for questions. All this time I did. Yeah.
Questions?
I figured out ask, are there any parameters or specific minerals within the bonding models that have given you any problems?
Let's see. Radicals.
Okay.
We have a hard time with radicals, and we may be able to do a correction for that, but the bond valence model is all based on the valence sum rule, which wouldn't apply to a radical, so that's difficult. But for condensed phases and things like that, it should be, and neutral gases, it should be fine.
Is there a way you could decrease the number of parameters by, say, maybe combining them into a single parameter?
Well, we can do that by looking at the distribution of the ideal values, doing the periodic trends and things like that, and coming up with models for that, and then predicting a value. But it's probably not going to be a really good substitute for refitting the model for a specific purpose.
How long does it take to run one of these models?
Oh, it depends on how long you want to run the simulation, because molecular dynamics simulations, that's where you just let the atoms move around, and then you do statistics on the behavior to calculate thermodynamic quantities and things like that. So it depends on what kind of computer. You can run them on a desktop computer. It depends on how many atoms you have in the system. You could do thousands of atoms on a desktop. Some people do millions of atoms on a supercomputer. And then it just depends on how long of a simulation you need. And that depends on what kind of information you need out of it, especially if you want to look at rare events and things like that. But, so you could be running it anywhere from a few minutes to a month. Yep.
So this model considers the repulsion and attractive energies, like cation, and anion. You said.
Yeah. So for instance, with bond valence, right, you have a bonded atom. If they get too close, that screws up your valence sums on the two atoms, right? And so if you have a spring on the deviation from the ideal valence, then that will cause a repulsion, right? And the same thing if you stretch it too much. There's a restoring force because it wants to, yeah. But the important thing about it is it's not focused on a single bond at a time. It's focusing on the entire bonding environment of a given atom. Okay.
So when using your Taylor series equation, what is like the highest exponential differential value you guys use?
You mean the multipole expansion?
Yeah.
So we just go out to the quadrupole moment, so
Okay.
third term.
Okay.
And we could, there are certain things involving, well, I won't get into what it's involved, but there are certain situations where we may need an octupole moment, but that's getting to such fine details it probably would exceed our ability to tell whether we were right or not, so.
What's the accuracy rate compared to using just the molecular mechanics combo?
Well, just to give you an idea for this plot right here, in the calibration set, which is a lot of different crystals that cover, you know, I had aluminum in 4, 5, and 6 coordination, silicon in 4 and 6 coordination, all kinds of different configurations. The average deviation, the standard deviation, I guess, was about 2 kilojoules per mole, which is astonishing. I mean, you could be off hundreds of kilojoules per mole easily with a normal molecular mechanics model, or even a quantum mechanics model, or a density functional theory model, or something like that. With the check set here, it was more, because we didn't calibrate on it, right? But it was still over this really huge range of energies. The average, or the standard deviation of the misfit was something like 12 kilojoules per atom, mole of atoms, right? So which is still really, really good. But again, we haven't implemented this, we've done all this in MATLAB so far. We're going to be implementing it in a program called LAMP, so we can do dynamics and things. Then we'll really see how it works in practice. Yep.
On your cumulative probability distribution,
Yeah.
It looked on the left that it was skewed in the black oxygen run versus on the right-hand side, right? So you have a skewed tail on the left. Does that mean the model is better at certain atomic things than other things?
So it's
The tail over there on
yeah.
the left.
So this one right here.
Yeah. Does that have like physical meaning at the atomic scale?
So it would be better at overbonding than underbonding, is what the skew is saying, I think. So, yeah, that fits. And so what that might mean is that, for instance, well, right here, deviation from the, well, this doesn't really show it. But what I'm saying is that it may not be a Hooke's law type thing where it's harmonic on both sides. It would be more like a skewed energy cost function. But so all this was just assuming or applying the valence summary of all these structures and then trying to fit the parameters of the valence equation to.
We should probably turn the classroom over to